So in this video, we are going to start by looking at moles calculations. So we're going to move on now to point 1.7.3 on our specification. We're going to look at moles and look at how we can use them in a calculation. So we're going to be starting on page 11. So over on page 11 now, let's have a look at what a mole is in terms of chemistry. And sometimes people get really confused about moles calculations or get really confused about what a mole is. But it's simply a particular amount of a substance. So it's an amount of substance. It's the chemistry word for saying an amount of substance. And it's very similar to saying a pair of socks. What do we mean by a pair of socks? We mean that we have two of them. And what if we said we had a dozen eggs? What would we mean by that? Well, we would mean that we have 12 eggs. So sometimes we use words to represent a number of a substance. So we might say a pair of socks, and by that we mean 2 socks. We may say a dozen eggs, and by that we mean 12 eggs. And it's just the same with a mole. A mole is simply a particular amount of substance. Now, the only thing is it's a slightly complicated number. So it's maybe not quite as simple as a pair is 2 and a dozen is 12. A mole is 6.02 times 10 to the power 23 of a substance. 6.02 times 10 to the power 23 of a substance. So if we had a mole of eggs, we would have 6.02 times 10 to the 23 eggs. It's just an amount of substance. So what does that number actually represent? Well, maybe you haven't done standard form yet, in which case I'll write this out as a real number. So 6.02 times 10 to the 23 means this. That's the number it represents. And in words, I don't really know what that number is, whether it's billions, trillions, bazillions, I don't know. But I know that it's a mole of a substance. So if you want to write that out to represent really how many particles it's going to represent, we're going to refer it to, you can do. It's 602 and then 21 zeros after it. So it's a massive, massive number. And it's because we're talking about amounts of substance, amounts of particles, amounts of atoms, amounts of molecules. A mole represents a large amount of atoms or molecules because atoms and molecules are so small. So you need to learn that definition. You need to learn that number. Again, I said to you in the first video, there's 2 definitions that are really important in this topic. There's the one we've already looked at, relative atomic mass. And that's a 3-mark definition. The definition for a mole is the other definition you could be asked within this topic, and it's worth 2 marks. So if you were asked what is meant by a mole of a substance, you simply have to write a mole of a substance is 6.02 times 10 to the 23 particles of that substance. If you get that number slightly wrong, if you write 6.08 times 10 to the 23, you will not get the marks. You must learn that absolutely exactly. So say that number out loads of times. Make sure you know how to write it in an exam. So this is a 2-mark definition. And I can almost guarantee that you will get either one of those definitions, either the definition for relative atomic mass or the definition for a mole. So when you come to maybe write your revision notes for this topic, there's not too much to learn as such, and there'll be a lot of calculations that you have to be able to do. But in terms of learning, it's a case of learning these 2 definitions and maybe learning some formula, like our formula for calculating percentage composition. And we're going to look at a couple of equations on the next page. But these are key things that you need to learn. For example, these definitions. So what is a mole of a substance? It's simply a particular amount of a substance, and that amount of substance is 6.02 times 10 to the 23 particles of a substance. So again, learn that definition word for word. So where does this number come from? Well, it's a number that we refer to as Avogadro's number, not an avocado, an Avogadro's number. He was a scientist, and that's something you'll learn a wee bit more about at A level. So essentially what we're saying is that if we have a mole of a particular substance, we have that many particles of it. So as you're given a few examples here, so if you had a mole of sulfur atoms, you would have 6.02 times 10 to the 23 atoms. If you had a mole of water molecules, you would have 6.02 times 10 to the 23 water molecules. If you had a mole of electrons, you would have 6.02 times 10 to the 23 electrons. Okay? One last link we need to make, and that is that the relative formula mass that we've been calculating earlier on in this topic, if we put the relative formula mass, we talked about it not having units, but if we put that in grams, it's actually equal to the mass of 1 mole of a substance. And that's actually the other way that you can put your definition of a mole. That would get you a mark as well, but I just think it's a little bit more complicated, a little bit more wordy. So the relative formula mass of a substance in grams is equal to the mass of 1 mole of the substance. So let's have a little think about that on what that actually means, because it is quite wordy. So if we were to look at a few examples here, say for example carbon. So carbon, if you look at it on the periodic table, it has a relative atomic mass of 12, and we can also say relative formula mass of 12 because it's just carbon C. Okay, so that formula has an RFM of 12. So if we were to put the units grams after it, so 12 grams of carbon, we know that we have 1 mole of carbon atoms in 12 grams of carbon. So if I was to literally get some charcoal or some other form of carbon and measure out 12 grams of it, I would know I have exactly 6.02 times 10 to the 23 carbon atoms there. If I was to take sodium, you saw me working with sodium in one of the previous videos on periodic table. If I was to measure out a mass of 23 grams of sodium, I would know that there's exactly a mole of sodium atoms there. I would know there's exactly 6.02 times 10 to the 23 sodium atoms there. And it's the same for compounds as well. So water we know is H2O. I'll write this down here. So if I was to work out the RFM of water, well, I've got 2 hydrogen atoms there, and they each have a mass of 1. They each have a relative atomic mass of 1. And I've got 1 oxygen atom there, which has a relative atomic mass of 16. So that's 2 plus 16, which is 18. So that's where the RFM of 18 comes from. So if I had 18 grams of water, I would know that I contain 1 mole of water molecules, which is 6.02 times 10 to the 23 water molecules. So if you're really bored today, get out a set of scales at home that you might use for baking, for example. Put a glass on it and zero the mass balance, zero the scale, and measure out until you have 18 grams of water. And you can say that in that glass you have a mole of water molecules, which is quite cool, I think anyway. So essentially what you need to know is that that key definition at the top of the page. A mole of a substance is 6.02 times 10 to the 23 particles of a substance. But also it links to the RFM, or the relative atomic mass, in that if we have the relative formula mass of a substance in grams, it's equal to the mass of a mole of a substance. So let's look at the periodic table for a second. So here's the periodic table that you should still have out in front of you. If you don't, then please make sure that you get it out, especially before we move on to some of these calculations. So let's pick an element. Let's pick iron. So for iron, its relative atomic mass is 56. So its relative atomic mass is 56. And if we were to just have iron on its own, its formula would be Fe. And so we could also talk about its RFM being 56. They mean the same thing for monoatomic elements. So what I'm saying then is if I have 56 grams of iron, that's a mole of iron. That's a mole of iron, in the sense that I will have 6.02 times 10 to the power 23 atoms of iron within 56 grams of iron. What about copper then? If copper has a relative atomic mass of 64, so if I had 64 grams of copper, that's a mole of copper. And I would know that I have 6.02 times 10 to the 23 particles of copper within that. So whatever formula you have, whatever element you pick, if you know the relative formula mass, the mass of that in grams is equal to the mass of a mole of a substance. And we're going to see that in the equations that we're going to look at now over on page 12. So this is over on page 12. Now, so from that knowledge that if we have the RFM of a substance, if we have that mass in grams, it's equal to 1 mole of a substance, we are actually able to derive this equation triangle. Now, you'll see it differently in different textbooks, and you can change this if you like. I represent N as the number of moles. But in some textbooks, you'll see that that is just written as moles. They'll write moles equals mass over RFM and so on. But I just use the term N. It's just a little bit simpler. And when we're doing calculations, it's a bit more concise. So this is our equation triangle for moles calculations. And if you're not a massive fan of physics, you might be wincing at this point thinking, oh no, another equation triangle. But the good news is this is the only one you'll have to learn for chemistry. So there's just one of them. And we'll do so many practice of this that you should know this equation inside out, even by the end of this video. So units are really important with this equation. So you can see there's N, which is given the units MOL. That's just short for moles, and sometimes in the exam they will literally write moles. So it doesn't matter if you write MOL or the full word moles, either is fine. This is really important here. Your mass must be in grams, and it highlights that down here. So it says remember to check that the mass given to you is always in grams. If it's not in grams, you'll need to convert it, and we'll come back to that in a second. So that's really, really important. And then finally RFM we know has no units. We've been working out RFM, like the RFM of water is 18, well it in itself has no units. So from the equation triangle we can get three equations. So hopefully you'll be familiar with how to use an equation triangle, but if you're not, let me take you through that now. So to get an equation from an equation triangle, what you need to do is cover up the thing that you're trying to work out. So let's say I'm trying to work out N. So let me cover over that. Okay, so I've covered over that. What am I left with? I'm left with mass over RFM. So it's mass, and then there's a horizontal line, and over RFM. So that means that N is equal to mass over RFM. So N is equal to mass over RFM. That's our first equation, and that will be a really important equation. Let's now try and get an equation for mass. So say I want to work out mass, I need to cover the word mass. So let me cover over that now and see what I'm left with. I'm left with N and RFM on the bottom. What does that mean? Well, if they're both on the same line, it means that I need to multiply them. And you may be more familiar with the bottom part of the triangle being just N times RFM. If you prefer to write it that way, that's absolutely fine, whatever way you would be used to. So if we're trying to work out the mass of a substance, we do N, which is the number of moles, multiplied by RFM. So it's N times by RFM. And again, that's going to be a really important equation. And lastly, if we want to work out RFM from this equation, although this is very rare to be asked to do it this way, but if we were asked to work out RFM, we need to cover it. And what are we left with? We're left with RFM is equal to mass over N. Mass divided by the number of moles. So with this, it's not as common to be asked it this way. I think there's one of the questions that you'll do later that you'll be asked to do it this way. But more commonly, we calculate RFM from our relative atomic mass values on the periodic table. So we'll make a quick note of that now. So we more commonly calculate RFM from the relative atomic masses on the periodic table rather than using this equation. So if you want to make a quick note of that in your notes, this equation is not often used. It's actually only really used if we don't know what the substance is, if we don't actually know what the formula of the substance is, and you'll see that later on in your questions. But generally, if you're asked to calculate the RFM of a substance, you do it from the relative atomic mass values. So for example, if you're asked to calculate the RFM of water, you'll be taking 2 times by your mass of hydrogen, which is 1, plus your mass of oxygen, which is 16, and that gives us 18. So more commonly we'll use those relative atomic mass values rather than this equation. So your two really, really important equations to learn, and again, these are the only ones that you use in chemistry, but are these first two. So first of all, that N equals mass over RFM, and second of all, that mass is equal to N times RFM. And it's up to you. You can learn the equation triangle, or you can learn those two equations. But actually, we're going to use them so much in the rest of this topic that you should be able to, you should have learned them by then. So one key thing I said was to make sure that the mass is always in grams. To be able to use this equation as it is, to be able to calculate the number of moles, the mass must be in grams. So if you have been given to it, given your value in kilograms or tons, then you must convert it. So for example, if you were given an industrial scale question, your mass might be given to you in kilograms or tons. And it says here, for example, in industry, masses would rarely be given in grams. Why not? Well, in industry, we're doing reactions on such a large scale that if we were working in grams, we would be talking about hundreds of thousands of grams, whereas it would be much easier to state the mass in kilograms. So for this, you just want to write that the reactions are carried out on such a large scale. Okay, so they're rarely given to you in grams because the reactions are carried out. If you want to write reactions are carried out on such a large scale. Okay, so you need to be able to convert from kilograms into grams. So how many grams are there in a kilogram? Well, there's 1,000 grams. So essentially what you're doing here is timesing by 1,000. So if you have been given a mass in kilograms, you must multiply by 1,000 to get it into grams. What about a ton then? Do you know how many kilograms there are in a ton? Well, there are 1,000 kilograms in a ton. So we've multiplied by 1,000 there. And then how many grams are there in a kilogram? Well, there's 1,000 grams in a kilogram, so we need to multiply by 1,000 again. So essentially, we're adding on 3 more zeros. So that's equal to 1,000,000 grams. So if you're given your value in tons, which sometimes you are, then you must learn that you need to multiply it by 1,000,000. Or you can think of it as multiplying by 1,000 and then multiplying by 1,000 again, whichever way you find easier. But learn that it's 1,000 kilograms, so that means it's 1,000,000 grams in 1 ton. So let's jump in and look at a few examples of these calculations before you try some on your own. So what I would always say is when you're given an example, make sure you highlight what am I being asked to calculate, okay? Because that will help us pick our equation first of all. So worked example 1 says find the number of moles of O2 in 8 grams of oxygen of O2. Okay, so it says find the number of moles. So I'm going to highlight that because that's what I'm being asked to calculate. And it says here that the first step is to pick the equation from the triangle, which has the thing you're trying to work out as the subject of the equation. What we mean by the subject of the equation is essentially that if we're trying to work out number of moles, it's at the start of the equation. It's number of moles equals. That's the subject of the equation. So let's go back up to our equations for a second. So it says find the number of moles of O2. So number of moles, what is that? Well, that's N. So what I'm doing is I'm picking this first equation, this equation 1, N equals mass over RFM, because that's what I'm trying to work out. So let me write that in our box here. So N is equal to mass over RFM. Remember, N is representing the number of moles. So that's the equation that I want to pick. So I'm going to need a mass, and I'm going to need an RFM. So I looked at my question to see what information I have been given. Okay, first of all, I've been given the formula. There's the formula of O2, and that's what I'm going to use to get my RFM. I've also been given a mass value, so 8 grams. It's my mass value, and what I need to check at this stage is it in the correct units? Remember, I need to have my mass in grams, and you can see that it's 8 grams, so it is in the correct units. So I'm going to give it a tick there, because it is in the correct units. So let's write out the information that we have first of all. Okay, so we are going to need the mass. So I'm going to write that the mass is equal to 8 grams, and I don't need to convert that. The RFM then, okay, so we need to work that out. So we can see that my formula is O2. So I'm going to put an RFM in brackets O2. So how do I work that out? Well, I work that out from the periodic table. And this is just as we were doing earlier in the topic. So again, make sure you have your periodic table out in front of you. You will need it for these questions, and you should be following along with me. So we're being asked to work out the RFM of oxygen. So what I need is the relative atomic mass of oxygen. So you can see it's O2, so we have 2 atoms of it. But we'll need the relative atomic mass, which we can see for oxygen is 16. So going back to our calculation now, we have 2 oxygen atoms, and each have a mass of 16. So it's 2 times 16, which is 32. So finally, I'm ready to put it back into my equation. N equals mass over RFM. So N is equal to mass over RFM. So the mass is 8. The RFM is 32. And put that into your calculator. Make sure you do put it into your calculator, because loads of people look at that and think, oh, the answer's 4. Well, it's not, because it's 8 over 32. So actually it's equal to a quarter, but we would write it in decimals. So it's equal to 0.25 mol. Or you can literally write moles if you prefer. So mol or the full word moles. So pick your equation. Check that if you've been given a mass, that it's in the correct units. Work out your RFM and then put it back into the equation, and make sure that you include units at the end of your question, particularly if you're being asked to work out the mass of a substance. Let's look at another example over on page 13. So worked example 2 says how many moles is 4.5 kilograms of calcium carbonate CaCO3. So again, first of all, let's highlight what we're being asked to work out. So we're being asked to work out how many moles. How many moles? So what's my equation for working out the number of moles? Well, number of moles is N. And what is N equal to? Go back to your equations on page 12. N is equal to mass over RFM. N is equal to mass over RFM. So I can see from my equation that I'm going to need a value for mass, and I'm going to need a value for RFM. So first of all, mass. Well, my mass is 4.5 kilograms. So that's my mass. Is it in the correct units? It's in kilograms. No, it's not in the correct units. So I'm going to put an X there, and I'm going to have to do something about that, and we'll come back to that in a second. RFM, what will I need for my RFM? I'll need my formula, which is CaCO3. And generally you're given the formula of these substances if you're being asked to do moles calculations. Because again, they don't want you, if you've got the wrong formula, you'll get the wrong RFM and then you'll get the wrong answer. So generally they'll give you the formula of these. Okay, so let's do a little bit of work on our mass and RFM. So we can see that our mass is equal to 4.5 kilograms. But that's not the unit I want it in. I want it in grams. How do we convert from kilograms to grams? We need to multiply by 1,000. So 4.5 multiplied by 1,000, put that into your calculator, should get you 4,500 grams. So if you want to write beside that somewhere that you need to times by 1,000, you can do. Okay, next we need to work out our RFM. And this time we're working out the RFM of calcium carbonate, CaCO3. So we need to do a little bit of work with this one. Okay, so again, periodic table in front of you. If it's not, make sure that you get it out in front of you. So we need, first of all, our relative atomic mass of calcium. So find that, it's in group 2. You should see that it has a relative atomic mass of 40. There's only one of them, so I can just simply write down 40. Next element along is carbon. Remember, you've got to separate out each individual element. So next element is carbon, and we can see there's only one of them. What's its relative atomic mass? Is 12. Okay, and then finally we've got 3 oxygens, so it's going to be 3 multiplied by the relative atomic mass of oxygen. So 3 multiplied by, this case it's 16. The relative atomic mass of oxygen is 16. Again, I'm just getting these values from the periodic table from the top numbers, just as we were doing in the first video. Again, this is making your relative formula mass calculation a little bit quicker. If you'd prefer to do it out completely, doing 1 times 40, working out what that is, and then 1 times 12, and then adding them all up, and that's fine. But if you're doing it this short way, just make sure you use brackets, because otherwise your calculation might go a little bit wrong. Okay, so if we were to put that into your calculator, or if you want to open it out, the brackets out first, it's 4 plus 12 plus 3 times 16 is 48. So our RFM is 100. And then finally we want to put that back into our equation. Remember, N is equal to mass over RFM. So our mass we worked out as 4,500. Our RFM is 100. Put that into your calculator. Again, it's worth putting it into your calculator just to be sure. But that should come out as 45 moles, or just MOL. It's up to you, MOL or moles. Okay, so with that example, we see the importance of checking that mass is in the correct units. If you hadn't converted mass, you would have got a different number, which would have been out by a factor of 1,000. And let's look at one more example, worked example 3. So it says, what is the mass of 0.35 moles of water, H2O? So this time we're asked, what is the mass? Or sometimes these questions are asked, how many grams are there? And grams we know are the unit of mass. And so that's how that could be phrased as well. So what is the mass? So I'm being asked to work out mass this time. So I need to choose the equation that has mass at the start of it, mass as the subject of the equation. So mass is equal to, and check over on page 12. Look back now and see, can you see the equation for mass is equal to? Well, mass, you should see there, is equal to N times by RFM. Mass equals N times RFM. And again, these two equations are going to be the most important. N equals mass over RFM, and mass equals N times RFM. And it's important that you get them the right way around. Otherwise, your calculations obviously will be wrong. So this time I'm going to need N and I'm going to need RFM. So N is my number of moles. And we can see here that's given to me in the question. So that's 0.35 moles is equal to N. The RFM I'm going to need to calculate, but I'll calculate that from my formula, H2O. Okay, so let's have a look at that now. So let's write down the information we have. We know that N is equal to 0.35 moles. Then we need to work out the RFM of water. So the RFM of H2O is equal to, well, I've got 2 hydrogens, so it's going to be 2 multiplied by the relative atomic mass of hydrogen. Look at your periodic table. It has a relative atomic mass of 1. Plus the mass of 1 oxygen atom. I've only got 1 oxygen atom there, so I can just write plus 16. So that's going to be 2 plus 16, which is 18. So we're ready now to put that into our equation. So mass is equal to N times RFM. N is 0.35 moles. Your RFM is 18. Again, put that into your calculator, make sure you're getting the same answer. So 0.35 multiplied by 18, you should get 6.3. But we can't leave our answer like that. We must include units. So think about the units of mass. When we use the equation, the mass always comes out in grams. Okay, so the mass always comes out in grams. And if you got a really big number there, like 63,000, then you can convert back to kilograms, and you can divide by 1,000 to get it back in kilograms. It's up to you, or the question might specify to give it in kilograms, in which case you would have to. But in this case, our answer is small enough to keep it in grams. So maybe write yourself a note there. Always include the unit at the end. So if you have followed the equation, the mass will come out in grams. So make sure you include that when you're doing your examples. So over on page 14 and 15, you have some examples of these types of questions. And this is what I want you to complete and then scan in your answers and send them to me, or send clear photographs of them to me. So page 14 and page 15, and you can complete these in your blue book or on file paper. So complete in your blue book or on file paper. When you're doing these calculations, I want you to show your working out in full, including the equation. So show your working out in full, including the equation, and then finally make sure you include units at the end in your final answer. So maybe write those things on the top of this page, and this applies to page 14 and page 15. So for example, if I was to show you how you were to set out question 1. So question 1A, for all of question 1, it says how many moles are in the following. So how many moles are in the following? Choose your equation first of all. So how many moles is N? Choose the equation for N, which is mass divided by RFM. And then I would separate these out. I would say, okay, well, what's my mass? And make sure you check that it's in grams. So you can see here, my mass of magnesium is 4 grams, and that is in the correct unit, so that's absolutely fine. The RFM then of magnesium, and we'll maybe put our formula there just to remind us that we get our RFM from our formula. On the periodic table, we're just looking simply for the relative atomic mass of magnesium, which is 24. So then I put it back into my equation. N is equal to 4 divided by 24. You don't need to do colour coding in all your questions, don't worry. And if you put that into your calculator, it'll come out as 0.16 reoccurring. So if you think that would be 0.16666 and so on. So if you were to round that to say 3 significant figures, that would be taking the 4th significant figure and seeing what it does to the one before it. So that would round that up to 0.167. And then remember, include your units in your final answer. This is moles, so we can either write as MOL or MOLES, the full word moles. Okay, so generally if you put these answers, if you can, to 3 significant figures. So you need to now answer all questions on page 14 and 15. And when you've completed those, scan them in and send them to me, or send clear photographs of them if that's not possible. And what I will just say is make sure you check a couple of things. Check the masses in grams. So check mass is in grams. And then also be careful with your RFM. So with all of these questions, you're given the formula of your substance, like CO2 or Al2O3. Just make sure you calculate your RFM really carefully, because if you don't do that right, then your calculation will obviously be wrong. So don't worry about the names of the substances. You've got the formula there given to you in each case, apart from a few examples in question 1 where it's just simply the atom. So it's just go to the periodic table, find the relative atomic mass of those substances. Okay, but where it's a compound or a molecule, you're given the formula. Okay, so give a go to those questions. If you're having any issues, then email me or send me a comment on the assignment, but hopefully you'll get on with these okay. But just to say, take them really slowly, do them really carefully, write them out in full, even if you don't want to, even if you want to take shortcuts, please write the equation out each time, because that will help you learn the equation. And once we've finished these, we're going to be moving on to slightly more difficult examples, and so it's really important that you know how to do these basic examples first of all, and that you're familiar with the equations, so that when we're doing the harder examples, you can recall those equations really quickly. N equals mass over RFM, mass equals N times RFM, and that you can do those really quickly. So be careful about them, take your time over them, because we will be using them in more difficult examples later. And just to really quickly show you page 15 as well, I expect these questions to be answered as well.